Hello, my name is Daniel Acuna. I'm an assistant professor at the School of Information Studies at Syracuse University, and I run the Science of Science and Computational Discovery Lab.
Hello, my name is Lijian Liang. I'm a PhD student at the School of Information Studies, Syracuse University.
Today, I will be presenting detecting biases in black box models using inspirations from psychology, which includes a demo in Python and code that you can run later on. What I will present is a paper that was presented this year in the FAT conference, Fairness, Accountability, and Transparency in Barcelona, Spain in January. Okay, so we have all experienced how much machines and artificial intelligence has improved over the recent years. And we can see that in our own cell phones. There are many apps these days that do all kinds of tasks that we thought only humans could do. For example, speech recognition. Now we can talk to our phone, be it Apple or Google, and it will understand relatively well what we are trying to ask. On the screen here, I'm showing you a task that perhaps embodies all of these ideas, the improvement of AI very rapidly over the last couple of years. So this is a task that is called object recognition. And the idea is that given an image that a computer can read, the computer has to return the list of objects that are inside that image. So here to the left, I gave an image to the computer and it told me, you know, these are the things that I think are part of this image. And it was pretty good. And it is pretty good. So object recognition has improved a lot, but it's hard to recognize how much this improvement accelerated over the last year. So here to the right, I'm showing a plot of years versus performance. And the performance here, the lower the better, is the error rate. So only in 2011, the performance was not really good. It wasn't really ready for production. And if you compare it to human performance, which is this red line here, the performance of the systems that were proposed, these are like the best systems proposed at the time, were not nearly as good as humans. What started to happening over the past couple of years is that new techniques and much bigger data sets and much better ways of training these systems started to appear. And a couple of years ago, we can see that the systems these days actually have better performance than a single human. Now, this is all good and powerful, but the problem is that many of these systems, due to their complexity, are really hard to introspect. It's really hard to understand what's happening inside. So what many times happens is that these systems are deployed. So for example, here on the screen, I'm showing a Google API that is available and still available, although they fixed some of the issues that I will present. So these systems are openly available, but because they're really hard to understand how they make decisions, it's really hard to detect issues that they might have. And these issues are only detected once these systems are deployed. So here I'm showing the API run on a hand and speedometer or some sort of temperature checker. And if you run, and again, this was fixed a couple of months ago, but if you run this, if you run this a couple of months ago, you will get that the system predicts that this image has a hand, which is correct, and a gun. Now, what these researchers discover is that if you change the color of the hand to be something more fair, then the prediction changed. So it was still saying that the most likely object is the hand, but the second most likely object changed from a gun to a monocular. Okay, so what's going on? So there seems to be a bias there, whereas we change something that shouldn't really affect the prediction. It is affecting the prediction, and it's affecting the prediction in a very significant and negative way. Well, what's happening is that in the past, we used to have systems that were relatively easy to understand for data scientists, for machine learners. So here on the left, I have a typical linear system. So basically, it's a system that takes the inputs that you use for your predictions and make a relationship between that input and the output. Okay, so here I'm showing in the x-axis this input, which in this case is gender, and the y-axis is the output. And you can see that there is a nice linear relationship. And then you can look at the model. So this is a linear model, and you can see that, well, if the model is taking the gender and multiplying it by a number, and that's the prediction. Okay, so you can look at this number and immediately understand how the gender is affecting the outcome. Okay, so if this number is positive, it means that the higher, or let's say, depending on how you qualify the gender, the higher this gender measure, the higher the outcome. Now, what's happening is that recently there are these techniques called deep learning, basically are highly nonlinear recursive functions that have the capacity to model phenomenon that is significantly more complex than what linear models used to do. So, but the issue is that once you have those complicated systems, it's really hard to understand how the input of the system affects the outcome. So here I'm showing, as an example, what's called a multi-layer perceptron, where you have multiple inputs, but they go through several functions that are generally nonlinear. So although you can see that the gender is being used in the function, because they pass through several functions recursively, then the outcome it's really hard to understand how the outcome is related to this input. And we have known this for a long time. We have known that the higher the accuracy a system has, the lower the interpretability. So in the past, we used to use systems that were significantly easier to understand for us data scientists. But as we have moved to depend on having better systems that provide accuracies that are high, we have removed some of that interpretability. So how can we, the question is, how can we improve the interpretability, or perhaps use systems that can detect issues even if the interpretability is low? Now, of course, we are not the first one to think about these issues. There are multiple groups working on this. The conference where we presented had multiple groups from the major companies that are dealing with these issues: Facebook, Apple, Google, IBM, Microsoft. And here I'm just showing two examples of tools that these companies have released, so that you can take models and run them through these tools to detect issues, perhaps even fix them. And this is another example of a tool to the right from Google. Now, the issue, or perhaps what we see in these tools is that, and we see in these conferences, is that they present ideas that are relatively new. Okay, so each group and each company is presenting different language, different terminology, different ways of interpreting the output, different ways of measuring biases and things like that. Okay, so what I will present now is to us a way of kind of making the language more cohesive and using ideas that are relatively old compared to the ideas that are being used for bias in AI. Okay, and by the way, there are other ways of solving this, not just with software. And that's the way that the European Union has been trying to solve this issue. So they introduced some legislation in GDPR where they force companies to offer an explanation. Okay, so they force essentially models to be more interpretable. But as we saw before, if you force something to be more interpretable, almost by definition, you will reduce the accuracy. So there should be like some discussion about what we want as a society. Do we want something that is accurate, but not as interpretable, or we want to, interpretability is really important and we're willing to sacrifice accuracy. So we took ideas from psychology and applied them to an AI, and there are some advantages to this. So the first one is that we take ideas that are proven, and the ones that we took actually are over 100 years old. So we know that they work. We have the experimental methods to run them. And also we have, which to us is very important, we have a language that is very cohesive and very coherent. Okay, so what is this idea? So I will show you what the typical psychological task that I'm referring to looks like. Okay, so imagine that you are being asked by experimental psychologists to solve this very simple two alternative question. Okay, so I show to you two tables, table 1 here to the left and table 2 here to the right. And I ask you, which of these two blue shapes, which of these two tables you think is bigger? Okay, so I'm going to give you a couple of seconds to think about your answer. Okay, so if you were to run this under proper experimental conditions where everything is, sorry. If you were to run this under proper experimental conditions where everything is controlled and you are quiet and everything is correctly set up, most people will tend to think that table 1 is bigger, that this shape is bigger than this one. In fact, what's happening here is that both shapes are of the same size. So I'm going to prove to you by taking PowerPoint and just moving the shape back and forth. Okay. And you can see that they are both of the same size. So what's happening here is that we as humans have a bias. And our bias is that things that have this perspective should be larger than things that are in this perspective. Okay, so we see something that looks like we are looking at it from a certain perspective, and our brain automatically corrects for that and thinks that table number 1 is bigger, but they're in fact the same size. Okay, so what we do with this, there is a task that is called the two alternative force task that allow us to measure this bias. And the way that we measure this bias with this task is by modifying the size, the area discrepancy between these two tables. Okay, so the area discrepancy between these two tables and alternative C is exactly 0. We know that as experimentalists. We know that they are 0. And what we do, we modify this. So we make them now the discrepancy negative. So the size of this table is smaller than this one. So when we take the difference is negative. And we can take something like this where this is even more negative. Now, what's interesting is that alternative B to humans will appear as exactly the same, even though we know as experimentalists that they are not the same. Okay, so if we plot the answers, so basically by asking humans repeatedly, which of the two tables you think is bigger, and by plotting that and by modifying the area discrepancy, we can form a curve. Okay? And this is what is called the psychometric curve. And in this curve, in psychology, we measure the bias by looking at what's called a point of subjective equivalence. It's basically where is the point where the two alternatives appear exactly the same. Okay, and here we can see that there is a bias because it's not exactly at 0. It's not where we think they should be. Okay, so what we'll do is we'll take this idea and this experiment and we'll adapt it to an AI task. And what we will do, we will take the word embedding research. And in this research, you have, okay, in this field, you have you have systems that have learned to represent words as vectors. Okay, so these systems are used for many tasks. You can use them for sentiment analysis. You can use them for translation and for many other tasks, usually natural language processing. And they are readily available in packages that you can download. Okay. What's interesting is that these word embedding systems are really powerful at representing relationships. So for example, if you want to understand the relationship between a man and a king, you can do so by taking differences between vectors. Okay. So, and what's interesting is that if you want to, let's say, understand the relationship of titles, such as a novel titles of being a king or being, you know, like the head of state, you can take the difference between king and man, and that will give you that vector. And then you can apply that vector difference to woman, for example, to predict what should be the title, what should be the kind of the elevated title of a woman, and it will give you something that is close to a queen. Now, we can take that idea and then create some sort of synthetic two alternative force choice stack. So we can create this artificial world where we ask an AI system to answer these two alternative force choice questions. So, and we have to be very specific on this, and we apply this idea to measure biases in word embeddings for occupations. Okay, so this is the basic idea. The basic idea is that we form a question that looks like this. We ask something like, what gender is this? And then we use an adjective that is gender. What is this, let's say, female or male? And here we put an occupation. So for example, plumber or hairdresser or lawyer, okay? Now, because we're using computers and here we have to give a word embedding of this adjective, we can modify it in any way we want, okay? So if I ask, what gender is this female plumber? Well, the system should reply female because I'm giving it exactly in the question. But if I modify this in some way, I make a mixture between female and male, for example, it's unclear what the system should reply. Okay, so if you think about it and compare to what I showed you before with the tables, we can form also a similar plot where we have in the x-axis this experimentally manipulated combination of things, and in the y-axis we have the answers. Okay, so I can modify the mixture of the objective from 100% female to 100% male, and then in the middle we'll have 50-50% female. Now you would expect, if there is no bias, that the system will be completely confused about the gender of the plumber if, let's say, we give like a 50-50% adjective exactly in between female and male. But actually what we found, and then this is the math to do that computation. It's relatively simple, and you can find it in the paper that I put in the title. But what we actually find well, here I'm showing an electrician, but basically what we find is that there is a bias. Okay, so the systems tend to switch from thinking from female to male before the 50-50 cut point. Okay, now it's a little unintuitive to read this, but this is basically saying that the system is biased against females, against women, because it tends to think that you need a little bit of maleness to switch immediately to think that this person is electrician. Okay, so if this point, the point that you are crossing over, is below the 50-50%, then you are biased against women. And conversely, if you are above 50-50%, you're biased against male. We can run this experiment, of course, for multiple occupations, and we did that. And you can plot, and then we do some manipulations where we look at the variation of this, and this is the average. Okay, so you can measure basically what is the bias in the word embeddings by using this technique. And here, on this side, you see occupations that the system tend to associate more with males, and here at the top you see occupations that the system tend to think that are more related with females. And this is validated. So basically, we took these biases, and they're highly correlated with how many people are working in these fields, the percent of female to male, and also the uncertainty in these measurements is also related to the actual number of people that are working on this. So in the future, we want to extend this idea. So all the things that we measure are readily understood by people that work in psychology. So it's really easy for them to understand what we are measuring in AI. So basically we're creating like an artificial psychologist that is measuring biases in AI. And we can apply the same ideas now to fix AI systems. And so we are, in this work, we are detecting biases, but there is nothing preventing us from fixing the biases and potentially taking ideas from psychology to fix artificial intelligence models. And that will be our next steps. So now I will leave it with Li Zhen, and he will go over an overview of the demo so that you can run it yourself.
Hello, I'm Li Zhen Liang. I'm a PhD student at Syracuse University School of Information Studies. Thank you, Daniel, for introducing the background and the theories behind using psychophysics to detect biases in AI. So to make the experience more tangible and maybe get your hands dirty, we have designed and implemented Python packages and a demo to show you how you can detect biases in Virtuvac model. So the demo is made public in GitHub repository. So as you can see in this repo, the folder Fair AI includes a code and package that you could use to detect biases. And we have also implemented a demo with Jupyter Notebook. If you can open this folder with your Jupyter Notebook, and you can detect biases by yourself. And now I will walk you through this repository. First, you need to install some packages that supports Fair AI. Then we can import Fair AI packages. And by using the low pretrain get graph 100 dimension function, we can download and load the 100-dimensional graph model to a Python dictionary. And the graph word embeddings model is considered to be the state-of-the-art word representation model. And after loading the word embedding model, we have also implemented a similarity function, which is based on the cosine distance between two embeddings. And as we can see, the similarity between man and king minus the similarity between woman and queen are very tiny, which validates the nature of the contextual nature of word embedding models. Now let's start detecting biases from this graph Virtuvac model. Now we wonder if the Virtuvac model have any biases towards gender and occupation. So as we run the model, we can see that when the point of subjective equivalent here is well over 50%, which means that when there's more woman vector in the nurse vector, the Virtuvac model couldn't decide whether the nurse is woman or man, which means that in a sense, the Virtuvac model are more likely to consider a nurse to be a woman. So after you have successfully detected one bias in this Virtuvac model, now you think other than thinking about just woman and man, I also want to do female, male, he, she. We can also do this at scale. Say that we have a long list of occupations and then several lists of pairs. We have also implemented a function called PSE. So after running the PSE function, we can get a graph of a long list of point of subjective equivalent. So each point here is the average point of subjective equivalent for each occupations. We can see that for this Virtuvac model, therapist, nurse, hairdressers are considered more likely to be a woman, a female, a she, while the scientists and electricians and engineer are more likely to be a man, a male, a he, according to the graph Virtuvac model. Now you can also compose your own list of target words and word pairs and try to find more biases by yourself. I hope you enjoy it. Thank you.